Assalamu alaikum everyone. I hope I am audible. Okay. So, as Zara mentioned, I am a software engineer at Arbisoft. I just like to code and try some stuff. Nothing much more interesting about me. So let's cut down to the topic. Today I will be talking about 3D point clouds. I was talking to some attendees yesterday in the conference, and I was a little surprised that hardly anyone knew about what 3D point clouds actually are. So I hope this talk will give you some perspective on it and make you a little excited about them. So what 3D point clouds actually are, in the simplest terms, they are the basic, most simplest representation of data in a 3D coordinate system. You could say they are a simple data structure, and you can say a matrix of n by 3. It can also be a matrix of n by 3 plus d, where d can represent any surface normal or RGB values, any kind of data that you would require in your use case. So each pointer denotes a specific location in a 3D coordinate system. This is Stanford Bunny. Whenever you start working with 3D point clouds, Stanford had 3D dataset. One of the first dataset that was regarding 3D that was by Stanford, and this is the Bunny. And it is when starting with 3D point clouds, you come across it and you start working on it. So first let's talk about data acquisition. We have gotten quite expert or efficient in capturing images, 2D data, you could say, but we are still not at that stage for, you could say, 3D data or 3D point clouds. We still require special techniques and special, you could say, equipment to get the data for that. Some of the techniques or equipment I mentioned, like LiDAR system that uses light sensors, photogrammetry, CAD model, structure from motion. I would suggest everyone to use LiDAR system if they are working with point clouds, because photogrammetry can introduce a lot of noise, which can be a real headache. So once you have gathered the data, you want to process and visualize it. I have listed down a few libraries in Python, like OpenCV, Trimax, Avista, and Cloud. They are really great at working with 3D point clouds. The most famous, you could say, the use is Open3D. It's also available in C++. So most of the people use Open3D when processing or visualizing point clouds. I have in the further few slides, I've just mentioned some of the processes or functions that you can use Open3D for processing point clouds. The first one is the visualization, just to visualize your point cloud. After capturing that, it has simple functions like visualization.draw geometries that you can just simply provide your point cloud, mention the zoom and all the other factors, and it will just visualize that point cloud for you. You can crop different subsections of the point cloud according to your liking. You can calculate point cloud distance with it. In this example, we have just removed that point, the cropped image, cropped chair that we cropped from the original point cloud, measure the distances, and just remove those points from the original point cloud. So you can do stuff like that. Outlier removal. As I said, there is always a lot of noise because we haven't gotten that efficient in getting the 3D data. So you always have to do some cleaning and pre-processing. So you have to remove outliers. There are two methods for removing outliers in Open3D. The first one is the statistical outlier removal. What it does, it just all the points that are at a larger distance than the average distances of the point cloud, it just removes that. We can give the threshold standard deviation ratio, and it will remove all the points. The points in the red are removed, considered as outliers. Outlier removal the second one is the radius outlier removal. It just sees, we can give it a radius. We have given, like in this example, 0.05. It will remove the point that have less number of points in the certain radius of their in the neighborhood. So in this example, it has removed those red points. We can also do some clustering in that, where we have just clustered the points that are relatively close to another. It just clusters them in groups. There are different functions, but in this method, I think it uses dbScan. Yeah, it uses dbScan for that, which is just density-based clustering. There should be a few examples like downsampling and normal estimation, which you also need when working 3-point cloud. Those functions are also available in Open3D. So once you have gotten the data and you have pre-processed and cleaned it, can you apply machine learning and AI to make it to make some smart decisions? In the traditional sense, it was not possible to apply machine learning or neural networks, deep learning in 3D point clouds. There were some techniques like people were using images of different views of the 3D point clouds and feeding them to deep learning neural networks, conventional CNNs to do some deep learning, but that was not really working with a 3D point cloud raw data. So the pioneer work on that was by a paper called PointNet that was put out by folks at Stanford. They showed that deep learning can be applied on the raw 3D point cloud data, and they demonstrated classification, power segmentation, and semantic segmentation. What's the issue with applying deep learning on 3D point cloud? As you would, I think you would know that neural networks, be it NLP or CNNs, they require data in a certain order. They can, if the order is changed, you will need to train the data again. You will need to train the model again. But that's the point. Point cloud data is not order; it is orderless. So you will need to train your model on your somewhat like n factorial permutations. That is not possible. So a model that does n factorial permutation should be really complex, right? Let's go through that. It's really simple. What they did was really clever. What they did different was that they treated each point in the point cloud separately. So n by 3 is our whole point cloud. They just fed it to some MLP layers, which are just fully collected layers of neural networks, and extracted some features out. So each point R3 space was converted to R 1024 space, and at the end of those fully connected layers was a max pooling. So that is also a permutation invariant function. And at the end of the day, they got a global feature of 1024 vector, and that encompassed all the global features of that point cloud. And they were then able to use it for classification, power segmentation, and segmentation networks. And it performed really well. The accuracy was really good for that. So that's how it was launched in 2017, and it has been cited like 10,000 times now. So there are some pros and cons to that too, because you are just looking at the global features, not looking at the local features. But research is going on. There was a paper called PointNet++, and other research is going on for looking into that too. But it was really this paper started the deep learning part of the point clouds. So let's start on some real world applications. How can you use 3D point clouds in real world? There are many applications: urban planning, environmental monitoring, like mapping the terrain, land surveying, architecture. You can like say analyze the integrity of some buildings. Robotics. You could just map the world in a 3D space and then do all that kind of stuff, decision making, like self-driving cars. Also utilize that. Agriculture, we will see a use case for that. Archaeology, you could say you need to preserve or digitize some archaeological sites, so it is also used there too. There is also one specific application I saw last night. It is also used in crime forensics, where they preserve the crime scene in a 3D by using 3D sensors. So it's really interesting too that it is also being used there. So the case study we have of agriculture, this is a project done between NUST and NARC, National Agricultural Research Center. In NARC, they analyze different crop health for different crops and between different seeds and their yield potential. So there are different features that they look at, but we just used height as analysis for the crop health. It is not that much precise, you could say, but we wanted to automate the process of this crop health analysis for them. So what we did was, because height is correlates to the yield potential, so we just used in the next few slides we will see how we use 3D point clouds to analyze the height of using 3D point clouds. So step one was to gather data, use a drone to survey the fields and create 3D point clouds. Clean up the data. It was a real mess to clean up the data because it was really noisy, but we were able to. I also mentioned some parameters that we used to clean up the 3D point cloud. And at the end of the day, when you got the height of the crops, you can create a simple regression model to predict the height of the crops in the coming season. This is a sample 2D 2D raster. Different color ranges represent different heights. Yeah, different heights of the crops, and you can see blue region is showing not optimal growth for the crops. The texture diagram looks something like this. Get the video from the drone, compute the point cloud, remove outliers, calculate the height. Calculating the height was a easy part. Just using a distance formula, you could just get the height of the. But there was some processing like averaging out and distance formula, etc. So, and then at the end of the apply to the regression model and get your 2D raster. And there was also a slide where we shown an application where it also at the end of the day it showed all the statistics of that point cloud, the estimated height, the actual height, the difference between the height of the estimation and the actual height. So the next is challenges. As I said, we are still not at that point like we are with the images or CNNs, but we are still getting there. The data is right now at the current state of the time, it is still very complex and data size is very huge. There is a lot of noise and outliers, but real-time processing is really hard. You need a lot of resources for that. Feature extraction segmentation is still a little, you could say, quite exhaustive process to do on point clouds. Feature direction could be with the new technologies coming out like AI and VR and Apple Vision Pros. There's also one thing that the new iPhones that you have, they also have LiDAR sensors. So you can create point clouds from your phones now. So if we get a little more, better in acquiring and processing the point clouds, it has a lot of industry specific like modeling, simulation, AI. If you integrate AI, AI can get really intelligent in the 3D space, you could say. So it is really exciting to see how it will evolve in the coming years. So that was all from my presentation. If there are questions, yeah, go ahead. Sure.
Right? One is for let's say if you have satellite images, what packages in Python would you use? Because it's very large scale data.
Yeah.
Can I do that on a local machine? And the second question is for your crop yield section bit, why not rely on traditional remote sensing technologies? Why are you going especially with point clouds and LiDAR in this case?
Remote sensing technologies were also an option for the crop health analysis. We just wanted to try and see how it will, how 3D point clouds will fare with them, and we got really good accuracy with it.
Better or like at par or?
So the thing is, for remote sensing, you need special sensors, which NARC did not have.
It is really well, right? To different types like Copernicus and Landsat. Not Landsat, Copernicus, for example.
Yeah, but Landsat data is not that in our use case, when we are height analysis, you cannot do that on a Landsat. Right. So that's why we use the drone and we had to generate a point cloud. What was your first question?
If I want to analyze satellite imagery,
satellite
LiDAR images, what packages in PyCon can I use? And can I do it on a local machine?
Local machine would be a tedious task. When we were doing point cloud analysis on, only a small set of field, it would take 2 to 3 days to process that.
Exactly.
So there are a few cloud. Yeah, so there are some packages that you could use, but they are paid, so you can generate. Some are free, some are paid, so you could use that for generating point clouds.
Because the big issue would be, like, say, for urban planning, for example, because you have such large images.
Yeah, that's true.
You would be stuck for days and days just processing it.
Yeah, as I said, we are not that efficient still, so hopefully in the next few years.
My question is, did you perform any analysis on the height of drone and its relation to the LiDAR industry?
Yeah, so that was also one case, but that's the beauty of 3D point cloud, that what you are getting is also both the 3 coordinates X, Y, and Z, right? So it is quite accurate as compared to with images you don't get the data, and with 3D point clouds that they represent a specific points, actual points in the 3D space. So the distance we did some inferring. We had to double check the height with the calculated height.
GSP thing. That in satellite imagery, this 1 pixel represent this much.
Yeah, you have to.
So how?
But with 3D point clouds, that's not the case. Once you get the data, you have.
As such, to say for the raster images, like not raster image, like I think what he's asking is, in raster images for satellites, you have a resolution like for the image.
Yeah.
So I think we can make it depending on the height.
Yeah, that was also a case. We had to do some processing for that too. Yeah, for the distance formula, you are correct about that. The angle and the height of the drone also contributed.
Representing how much meter?
No, the tool you use for visualization has some units in it, and then you have to do some processing to convert it to centimeter or meter or feet according to your. Thank you, everyone.